Hello students, this is the third lecture of the fourth module wherein we were discussing about software optimizations with underlying hardware in view. In this lecture we are going to look and try to answer one question on how we can improve the locality of the program. A quick recap that we have seen right at the beginning of module 3, we were saying that the entire memory hierarchy works or is built based on the principle of locality. It has two aspects to it. One is spatial locality, other is temporal locality. Now with that in mind, whenever we set out to write a program, because the underlying hardware expects good locality or works well if the program has good locality, it is our duty to ensure that the accesses have some notion of locality in them. The levels which are closer to the processor pipeline are typically small and fast, so any access that is a hit in these closer levels would be faster. On the other end, the levels which are farther from the processor are slower and huge in size, like our DRAM and SSDs. So as programmers, we should acknowledge that there is a hierarchy of memory and not everything is readily available to the processor pipeline for it to continuously process the instructions and assume that the loads and stores will finish in one cycle. It's not the case. With this realistic point in mind, we should write programs so that the data reuse will be there. Like I have mentioned, if many data accesses are hit in the closer levels, then we will have better performance. Also, the smaller caches consume less power than the DRAM or SSD. So we are not only improving the performance, but we are also consuming low power. So with this question in mind, the important task we have is we need to visualize how the data accesses would be at various levels of memory and try to optimize those accesses. So let's look at one simple example to begin with. Let's say we have a function sum vector which takes a vector v as its input, and all we do is we sum all the elements of the vector and return the final sum value. Now if we want to look at the way the accesses would be, let's assume for the discussion that the underlying cache line or cache block size is 16 bytes and integer takes 4 bytes. So typically a cache block will have 4 elements of this vector. So if we look at the v of I for I equals to 0, 1, 2, so on and so forth, the access order would be something like this. When I equal to 0, the very first iteration of the loop, we would be accessing v of 0, and this is the very first access. It's a cold miss. So the first element will not be available. So we send the request to the lower levels of cache, and because the cache block size is 16 bytes, we get v of 0, v of 1, 2 and 3 together. So in the second iteration, when we are trying to access v of 1, it is readily available in the cache, so it would be a hit. In the same way, v of 2, v of 3 will also be hits. Now v of 4 again will be a cold miss, and the pattern would repeat. So for every 4 accesses to the cache, there will be 1 miss and 3 hits. So the hit rate would be somewhere closer to 75%. This would be the way an array would access. And missed to mention a point, by default, the way data is organized in memory is in row major format. It would mean that the elements which are in the same row will be belonging to the same cache block rather than same column. So we will have a better understanding here in the next example. Now we are looking at a matrix A m cross n size, and we are doing the same operation of summing up all the elements here and returning the value, final value. So if we try to visualize the way accesses would be across multiple iterations of the loop, we have the outer loop of I and the inner loop of j, and we would access a of I and j from 0 to n. It means an entire row of elements of a. So in the very first iteration, I equals to 0 and j equals to 0, it will be a cold mess, and we would bring a of 0 0, 0 1, 0 2 and 0 3 from the lower levels of cache or the memory. So the next three iterations of the j loop will be hits, and the fourth and the fifth iteration of the j loop, again we will have a miss followed by 3 hits. Now when let's say for example the value of n is 8 and m is 4. So when I equals to 1, we have come to the second iteration of the I loop. Again a similar pattern would be seen. The very first element a of I comma a of 1 comma 0, sorry, a10 would be a miss, and 11 12 13 would be hit. Again 14 will be a miss, 15 16 17 will be hits. In the same way the other two row accesses also. So overall the hit rate again is somewhere closer to 75%. Now this was one of the cache optimizations that we have seen. If we increase the block size, let's say instead of 16 bytes, if we have considered a block size of 32 bytes, when there was an access for A00, we would have brought the all the 8 elements with us. So in that case, the hit rate would be much higher. Of 32 elements that we were trying to access, only 4 would have been misses. So it is the hit rate would be 28 upon 32. But we can't indefinitely keep increasing the cache size. So typically the cache size of most of the current processors is somewhere between 64 bytes to 128 bytes. Moving on, let's look at another function which also sums up all the elements of the matrix A m cross n, but we have changed the loops. The outermost loop is j, the innermost loop is I. If you look at the way the accesses would be, the very first access would be A00, and we would have brought these 4 elements to the cache. But immediately in the second iteration of the loop, of the I loop, we would access A10. So again it is a miss, but we would get all these blocks into the cache. A20 miss, and 4 blocks, 4 data items into the cache, and A30 will be a miss again, and would have brought these 4 elements into the cache. Now let's assume that the cache size is only 16 of these array elements. In that case, when we are in the second iteration of the loop, when of the j loop, we would be trying to access or to aggravate let's take the worst case scenario wherein the cache capacity is only one block, for example. In that case, the J0 A01 will be a miss. So we bring in 4 blocks again, and A11 will be a miss, A21 will be a miss, A31 will be a miss, and the other loop iterations overall effectively will lead to miss accesses all through. So the hit rate would be nearly 0. If we run them on the actual hardware, there was an observation that some array rows is almost twice as fast as some array columns, and this is more or less just because of better utilization of the cache. Because if the hits are observed at the L1 cache, then the pipeline will not stall and we will have better performance. Now this was summing the elements of the matrix, and here we observed that if we have changed I and j loops, the performance was drastically different. But what about the matrix transpose operation? So here there is no definite thing or specific improvement if we do I and j or j and I by interchanging them. So the effectiveness of cache utilization for a matrix transpose is not so straightforward as the examples we have seen. But matrix transpose is not of our primary interest. For now, we would look at a much more popular operation on matrix, which is multiplication. So let's say we have a 2 cross 2 matrix A, or matrices A and B, and we would calculate C. We need to calculate C, and the typical program that we would write, have labeled it as version ijk because of the way the loops are arranged. We have the I loop first, followed by j, and followed by k. And here we have already did the reduction in strength part. We are calculating sum across all the for one particular row and eventually writing that to the actual C. So we have reduced a lot of loads and stores here already. We would need the order of this matrix multiplication is n power 3. We would need to access the elements of A and B and access the elements of C every time. So n per source element, and L values we would be needing to sum and for the matrix A, the accesses with this loop structure of I, j, k would be that all the elements will be accessed in row. When we look at matrix B, the accesses would be 1 per column. So if we try to visualize the way accesses would be, we would pick a row of A and a column of B, multiply element by element, sum them up, and we would write as Cij here. And like we observed in the previous example, access to A would have better hit rate in the cache than access to B. Here because of the cache block size, we can have hits in the remaining accesses of the same block, but that will not be the case for B. So if you look at the inner loop, which is the K loop, for every 4 accesses, we would have 1 miss in A, so the miss rate is 0.25%. Every access for the column element of B would be a miss, so it's 100% miss rate. And because we moved the sum out of the loop itself, there are as such no accesses to the element C. This is for the K loop. Now let's try to rearrange the loops as earlier it was ijk, now it is jik. So the j loop first followed by I and k loop. We have again changed the indices also accordingly. So if we try to visualize the accesses, there is not much difference, because for every element of B we are accessing all the elements of a row in A, and we are calculating one element of C. So the misses in the innermost loop are similar to what we found earlier. There will be one miss for every 4 accesses in A matrix. Every access to the B matrix would be a miss, and there is no access for the C matrix within the innermost loop. So the performance of ijk and jik would be more or less in the same range or comparable. Let's try out other combinations of the loops also. Let's look at version wherein the j loop is first followed by k and followed by I. The innermost loop is I now. If we try to visualize how the accesses would be, now we are accessing the A matrix column wise, because we are looping for every iteration of I, we are moving to the another element of A. So the accesses are column wise. We are accessing only one element of the B. Before we enter the I loop itself, we have kept it ready available to us based on indices K and J, and we are calculating an entire column of C. Again, the behavior of the C matrix would be same as A matrix with respect to the cache. So every access to the cache for A matrix would result in a miss. We haven't accessed B matrix in the inner loop, so it's 0. And C matrix, every access to the element of the column of C would be resulting in a miss. So when compared to the previous two arrangements, this arrangement has more misses. Another arrangement of KJI here. So this also has a similar performance as the previous IKJ. So I is the innermost loop followed by J, and the outermost loop is K. And similar to the last version, the C version, the innermost loop will be accessing the matrix A, one per row, an entire column. There is no access for B, so there are no misses for B, and the C matrix will also be accessed column wise. So the performance of C and D versions would be more or less similar. Now let's try to look at another version, Kij. Here the K loop is the outermost followed by I and J. It would, if we try to visualize the way matrix elements are accessed, we are picking one element of A, multiplying it with the elements of one row of matrix B, and we are accessing one row of elements in C, or writing to one row of elements in C. So if we consider the innermost loop, which is J, there is no access for A. For B and C, because it is in row measure format, if you consider the cache block size of 16 bytes, we would have only one miss for every 4 accesses. So the miss rate is 25%, or the hit rate is 75%. Another variant is IKJ. I have already put the way the access would be. We have the I loop as outermost loop followed by K, and the innermost loop is j. Just like the E version, here we are accessing an element of A, multiplying it with individual elements of a row in B, and generating a row of elements in C. So the accesses would be something similar to the E version. Matrix B would experience 25% misses, and C would also experience 25% of misses in its accesses. Now, if you look at the overall picture, let's look at a small table wherein we have summarized everything. On column A, we have the version. The second column is number of loads per the innermost iteration, followed by number of stores, followed by number of misses in accessing matrix A, B, C, and overall total number of misses per iteration. I, J, and K, IJK and JIK have similar performance. We would load two elements and we are not storing any element, so there is no store here. JKI and KJI, we are loading two elements and we are storing one element. And here the miss rate, we have already seen that both A and C have almost all the accesses as misses. Kij and Ikj, we would load two elements for the innermost iteration and we would store one element in the C matrix. So here B and C experience 25% of their accesses as miss. Now if we look at the overall miss rate, out of the three accesses, we would have 1.25 misses. Here two of the accesses would be miss, and here out of the three accesses only 0.5 of them would be a miss. So when run on the real system, if you look at the increase in the matrix size from 50 to 750 here, and on the x-axis, on y-axis it is the number of cycles that were required for each inner loop iteration. From the previous table itself, we could estimate that JKI and KJI would behave versely, and that's what shows here. This is the graph for those two. The next is we have 1.25 misses for IJK and JIK, so which are here. And the best case is we have only 0.5 misses for KIJ and IKJ. Now if we consider a matrix size of, let's say, 750, and let's say the best optimizations are taking somewhere between 4 and 5 cycles, and the worst versions were taking somewhere between 50 to 55 cycles, we have already achieved 11% of 11 times improvement in the performance, and here somewhere 4 to 5 times when compared to the IJK and JIK loop. So just by rearranging the loops, we have order of improvement in the program performance, and this is primarily driven by the improved accesses to the cache. What we have done with rearranging the loops was try to increase the spatial locality, wherein we were trying to access the adjacent elements of the matrix right one after another. But typically the matrices we see in the real life don't have small sizes that we would imagine, typically there will be tens of thousands of elements. So it can be a 1000 cross 1000 matrix. Now, if we are considering such huge matrices, would a simple loop interchange be sufficient? The answer is it's good, but it's not sufficient. We can do slightly better. That's what we are going to look at here. What we have tried to exploit in the small cache is the spatial locality, like I have mentioned, and every fifth access to the cache will lead to a miss, and which might typically lead to 10 plus cycles of stalls in the pipeline. Now, because we already got the 4 elements in the cache, the question is, can we use them better? Here comes the temporal locality part. If we have brought a data item or the cache block with 4 data items into the cache, before we kick out the block to the lower level of the cache, because of the limited space that we have, we should make maximum use of it. So let's see how we can do that. The technique that's used is called blocking. Some of you might already be aware of this. It's a very popular technique to speed up things. Blocking is typically applied to the innermost loop so that the temporal locality improves. So this is our matrix multiplication program, which is popularly called as DGEM program, and it's the core of many of the neural networks that we see today. And if we look at the way the matrices A, B, C are accessed, it would look something like this. So for a row of accesses in A, we would access a column of elements in B, and we would generate a row of elements in C. That's pretty straightforward thing. That's what we normally do. But how was this program optimized? With blocking is what we'll see now. So here is the optimized program with a block size of 32. Here is the main function of sj, si and sk loops, and they call the function doBlock with these parameters as inputs, and also the size of matrices and the matrices themselves. And within each of this block, we are doing the typical matrix multiplication that we have seen just in the previous slide. So what happens here is we are taking a block of elements of matrix A and B and generating a block of elements of matrix C. So here we stop visualizing that once we access a row of matrix A, we are going to access all the elements of row. We are going to access a part of them which belong to the block. So this is how the accesses would be. For an access to the row of A, we are going to partially access few of the columns of B and generate few elements of C. And just like the factorial program that you have seen in the Lec3, even though it looks little straightforward, no matter how much I explain, you can't understand it completely. So I would strongly suggest you to write this program and try out yourself. You can't keep staring at a code to understand it. So the best way is to get your hands dirty. So with blocking, one obvious point is the simple matrix multiplication program ended up looking like this, which is not so straightforward to read or understand, but it is a standard optimization. So once you understand it code by looking at the code, whenever you find such an opportunity, you will be able to employ blocking. So the performance of blocking when compared to the previous simple loop interchanges is something like this. Here we have the matrix size, and here we have the cycles per iteration, and the blocking versions of ikj and ijk are somewhere here. The main takeaway is the performance improves by a factor of 2 when compared to the previous two best versions of the matrix multiplication. Also, if we look at the way the performance of the blocking is, with an increase in the matrix size, more or less the performance is consistent. It's not increasing with the matrix size. So it independent of what the block size is of the cache block size is underneath and what the actual matrix size is, if you go for blocking, you are more or less assuring that the maximum performance for this matrix multiplication is achieved. So in summary, the first point is look for rearranging the loops in order to improve the sequential accesses. That is, we are trying to improve the spatial locality by using stride of 1 to the best. Focus on the inner loop and try to maximize the temporal locality and try to increase the reuse distance. Try to increase the data reuse, and therein we saw blocking. Overall, the summary of this module is, first we have looked at small optimizations like code reuse, reduction in strength, and studying the code to avoid any unnecessary memory references or accesses. In the second lecture, we saw two of the compiler optimization. One was the static pipeline scheduling, wherein the compiler was identifying the data dependencies and control dependencies and creating enough distance between the producer and consumer by inserting safe instructions into them such that the stalls in the pipeline would reduce. Following that, we have seen loop unrolling and strip mining within the loop unrolling. Today we have seen that rearranging the loops would increase the spatial locality and blocking would improve both the spatial locality and temporal locality. So with that, I'll quickly summarize what our role as programmer would be. Here we are trying to answer the question on how better can I write programs if we already have an optimizing compiler at our disposal. The first one is what not to do. Don't write code that it becomes unreadable and it becomes difficult to maintain or extend in future, or even we might end up in a situation where we cannot ensure the correctness of the program, whether it's working correct or not. So what we would need to do is pick the best algorithm, write the code in a modularizable way which is both readable and maintainable, use procedures and function calls or recursion, and try to minimize the usage of existing libraries and write an efficient version yourself. These factors sometimes might slow down, but when you look at the program yourself, you will understand it. Eliminate any optimization blockers because of using the pointers or function calls, because the compiler is very limited in its potential to resolve these. Following that, focus on the inner loops of the program. Do detailed optimizations where code will be executed repeatedly. Those are the loops typically. And look at the way the access would be and try to get a performance gain from them by unrolling or blocking or rearranging the loops. So here is the reading assignment for the fourth module. Overall, I've specifically mentioned the sections that you would need to read in the reference book that I have already shared the link with you. You can avoid the middle sections, but if you feel there is a discontinuity in the flow, you can read through the omitted sections also. In chapter 6, this is where the authors deal with the exploring or increasing the locality part of the program that we have discussed today. Just these three subsections in chapter 6 would suffice. And for memory blocking, I know I haven't spent much time on it because I strongly feel you need to try it out yourself. The explanation is in our CO and design textbook by Patterson and Hennessy. So with that, I conclude this module. Thank you.